We have already had many episodes where we read assembler code and reverse engineered how a program works, and we even have written our first exploit by using a buffer overflow vulnerability in a program written in C. In this code I want to show you how you can learn how to read assembler produced by C code yourself. The idea is simple. Just write some C code with different C language features and then look at the assembler code that is produced by compiling it. This is often part of normal research. For example, listen to what Ian Baer from Google Project Zero says during a talk about his research on inter-process calls on OS X.
One approach to reversing or to understanding how this kind of thing works would be to sit in IDA and just reverse the serialization and deserialization code and slowly build up a picture of how it works. But another kind of quite nice way to do it is just write a test program to send little messages and then find the right place using LLDB to break and just start dumping hex.
So because he had to understand a fairly complex data structure, he simply wrote a test program to analyze it, instead of reversing a full application. Or there was a talk and a paper from Black Hat USA in 2007 about how to reverse C++ programs by looking at C++ concepts and how they look like in assembler. So now I have created 3 different C code test cases, and you can find them in my GitHub repository, or just write it yourself. One is about variables and data types, one is about function calls, and one is about control flow stuff like loops and ifs. So let's start with the variables.c. First thing I want to point out are those triple X's. Those triple X's are defined as an assembler NOP instruction. The reason for that is later when we look into the disassembly we can find those NOPs which are separating our tests, and that is pretty neat. So this makes it easier to see which line of C code is responsible for which lines in assembler. I will not go over every single test, this is something you could do yourself. Simply pause the video at certain points or clone the repository. Anyway, let's get started. First we define a couple of numbers, unsigned and signed, integers and floating point numbers, and different sizes with UN32 or UN64. The latter is important because normal integers might have different sizes depending on 32-bit or 64-bit architecture, so it can lead to bugs, so better use data types you are guaranteed to get a certain size. If you want to learn how to program C properly, there's a great article called How to C as of 2016. After that we create an array with 32-bit unsigned integers and we access one of the elements of this array. Then we look at a single character and then also a string. And maybe you know that a star means pointer in C, so we are defining a variable that is pointing to a string. I have added a makefile so you can simply type make into the terminal to compile our files, or make clean to remove the binaries. This will create a 32-bit and a 64-bit version of the variables program. But as you can see, I get an error trying to compile a 32-bit version with -M32 on this 64-bit machine. So I have to install the 32-bit libraries first to be able to build the code. After installing those, the build works fine. A makefile is just a little script that defines how a project has to be compiled. So let's open the code, 32-bit and 64-bit version next to each other in GDB and disassemble main. And also open the code. Okay, now let's look at the first integer examples with negative values and signed and unsigned values. First of all those local variables are stored somewhere on the stack. You can see that because they are referenced relative to the base pointer. Then you notice that the assembler code doesn't know negative numbers. They are FFF something. If you are interested how negative numbers are displayed, watch my 10th episode about numbers. And also, there is no difference between variables that are signed or unsigned. But there's one interesting difference between 32-bit and 64-bit code, because we define one number to be 64-bit long, but on 32-bit the registers are only 32-bit. So if you want to write full 64-bit, you have to write 2 times. The floating point numbers are also interesting because they got stored somewhere else in the program and that value is then moved into the local variable. The array is also interesting. We created an array with 10 values, but only set the first 5 values to a default value. As you can see, those values are stored on a stack, and then it moves from that location on the stack to the real array location. Instead of writing it directly to the array, it does it this way. No idea why. And you can see down here when we reference the third entry, so you can see that this is the real location of the array on the stack. Next come the strings. You can see that a character is just a byte. It doesn't matter if we have an unsigned int with 8-bit or a char, it's the same. And strings are also referenced over an address. So the local variable is not an array of characters. The local variable contains an address pointing to a string. Now let's have a look at the control flows. Open it in Radare, analyze all, seek to main function, and enter visual mode. First we set a variable to 0, and then comes the if. This is done by loading this local variable into a register and comparing it to hex ff, and then jump if it was less or equal, so you can see which branch it may take. Then comes a while loop. We load the local variable again in a register, compare it to a value, and either jump inside the block or leave. And inside the block we load this value again, increment it, and write it back. Now compare it to the for loop. It's basically the same. We start by setting the variable to 0, then we compare it if the loop condition is still true, and inside the loop block we can see our knob, and at the end of the block we increment the variable by 1. Exactly the same like the while loop. So you can see that for and while loop in C are basically the same. Next, let's have a look at how functions are called. Again, open both the 32-bit and 64-bit version. First thing you notice that the 64-bit version moves 0 in EAX, no idea why. Otherwise the function call looks the same. Except look at the addresses. If you have no ASLR, then 64-bit code is generally at hex 40 something, while 32-bit code is at hex 80 something. Knowing stuff like that is helpful, because if you see an address with 40 something, you know immediately that is pointing into your code. So the next function returns a value and we save it in a variable. And you can see that in both cases the value is taken from the EAX register. Okay, so apparently return values are handled via EAX. Now function 3 is interesting, because we pass a parameter to it. In 32-bit you can see that the value is loaded from somewhere and then stored on top of the stack. And then the function is called. But on 64-bit we see that the value is loaded into the EDI register. This is our first big difference. Functions in 64-bit seem to be called with parameters in registers, while in 32-bit the parameters are stored on a stack. Next function uses two parameters, and again, you can see how 32-bit just places the value on the stack, first parameter on the top of the stack, the second a bit further down, but in 64-bit you can see that it uses ESI and EDI for that. Now we get curious, what does 64-bit do when we have so many parameters that we cannot keep them all in registers? First of all, 32-bit code again. You can see how the parameters are stored on a stack, and the first parameter is on top of the stack and the last value moved. That is what we would expect. In 64-bit we can see that the first couple of parameters are stored in the registers EDI, ESI, EDX and so forth, but from the 7th parameter on they get stored on a stack as well. Awesome! Now you can identify all kind of different assembler patterns. You don't need a decompiler all the time. You can do this all in your head, and when you reverse more and more programs, those patterns become more easy to recognize, and you will not feel overwhelmed again with the mass of weird instructions. You will be able to scan over a function and say, here's the local variable, then calls this function with the variable as a parameter, and then the return value is used in a loop. And you can use this same method to understand how different disassemblers like Hopper, or Radare, GDB display code, or for example how different the AT&T assembler syntax is from the Intel syntax. I hope you have a lot of fun next time reversing a program.